Is it recording? I think so. It's supposed to have like a, say, the red button, right? On the screen. I'm not sure. Let me see.
เลคคอร์ดเหรอคะอาจารย์
Record นะ Okay, thank you.
ค่ะ
แล้วกลับไปยังไงล่ะเนี่ยสวยละ Hold on. All right. All right. So what I'm trying to say is that transport phenomena is actually all around you. Okay, it's not just like chemical engineering thing that you cannot see or feel. It's just something all around you. Because sometimes when you talk about, let's say, thermodynamics, it's very, very difficult to understand, right? And you don't really know what thermodynamics have something to do with anything around us. But transport phenomena is something closer to us. Okay, so in just a second, you will be able to understand more clearer about these pictures here. What transport phenomena is involved in this. Okay, so. All right. The previous slide is something that is just all around us, right? In reality, but in terms of a chemical engineering applications, do you know what these are? It's some kind of a flow in tubes, in pipes, right? Yeah, one is slower, the other one is more faster. One on the left hand side is more like a laminar flow. On the right hand side, it could be like turbulent flow, right? So yeah, it's something with the transport phenomena, of course. And what about this thing? We have like some kind of a mixing tank or a reactor, right? We have 2 feeds coming in, mixing, and the colors change, right? Yeah, so there's something going on in there, okay? And there's also another type of reactor. We have a feed of some kind of a gas bubbles into the liquid phase, okay? And the other one, anyone know what this is? Some kind of a heat exchanger, right? It's the plate heat exchanger. Okay, so we have the hot stream coming in and also the cold stream coming in, exchanging the heat. Okay, so you can see a variation of applications that are involved with the transport phenomena. So transport phenomena is like a fundamental knowledge that's used in designing and also in terms of operation for chemical engineering applications. Okay, so in the next 2, 3, 4 weeks, I think you will get a better understanding in terms of transport phenomena with the chemical engineering applications. Okay, so let's come back to the definition of the transport phenomena. Okay, what is it? And let me show you in terms of the example that will make you understand clearer. Okay, so if I have a closed system in a box like this, okay, and then at the beginning, this system has a temperature of T. Okay, so it has a uniform temperature T. So if you take a thermometer and measure it anywhere, it's going to be at temperature T, okay, anywhere. So then if I apply heat on the left-hand side to the closed system right here, okay, so what's happening is that in terms of thermodynamics, have anyone taken thermodynamics class before? Last term, right? Last semester. Maybe some of you might be taking this term. So in terms of thermodynamic course, okay, we're going to do a little bit of a compare, a little bit, so that you know that chemical engineering in different classes, we have the same approach, but in details, it's a little bit different, okay? In terms of thermodynamics, they see this closed system as a macroscopic view. It's like this is the whole system. So if you measure the temperature, it's going to be temperature T anywhere. Okay, the temperature is going to be uniform in a whole system. But in terms of transport phenomena course, Since transport phenomena, we do the microscopic view, okay? Unlike the thermodynamics, okay? Like I said, the thermodynamics, we look at the big picture, like a whole system, okay? So anywhere the temperature will be equal to T, even if we apply heat, okay? But in terms of transport phenomena, we take a look at specific area. So that means that the temperature in this closed system is not going to be uniform. It's not going to be equal, okay? So what I'm saying is that the temperature is going to be distributed because the heat comes in on the left-hand side right here. You can imagine that the temperature on the left-hand side should be higher than that on the right-hand side. Is that right? So if I make a plot, okay, in terms of the distance in the x-axis right here, and the temperature is on the y-axis. So can you imagine what the graph will look like? It's going to go down, right? So it's going to go down something like this because we apply heat on the left-hand side, okay? And on the right-hand side, since the heat is trying to dissipate, okay? So it's going to be lower than the left-hand side, okay? So here is the the definition of the distributed temperature in the closed system in terms of the transport phenomena. All right. And what I'm going to add is that this temperature distribution along with distance here is going to change with time too. So if you keep applying heat on the left-hand side for a whole day, for example, okay, do you think the graph will be changing or is going to be constant like this? It's going to change, right? And what is it going to change? What's it like? It's going to be like a flat, right, curve, okay, like a horizontal line, because it's going to reach steady state, okay? So here, temperature is going to change with position. In this case, is the distance and also with time, all right? So yeah, this is the definition in terms of the transport phenomena. So you can see that even if thermodynamics and transport phenomena, we are in the same approach, but the way we look at things is differently, okay? Thermodynamics, we look at the big picture, it's like a macroscopic view, okay? Temperature T. If we apply heat and then it reaches the steady state, then the whole system here has the same temperature. But in terms of transport phenomena, we take a look at the specific area, okay? So the temperature is not equal within the system, all right? So what is transported? Like in the previous example here, you can see that heat is transported, right? So it can be something else that can be transported too. In chemical engineering, there are 3 types of things that can be transported. The first one is energy, just like the previous examples, okay? The second one is the mass, okay? Because mass can transport it, like this thing, right? You can move it around too, okay? And the last one is the momentum. Do you know what momentum is? Momentum, what is it? Huh?
concentration ไหมคะ
Sorry?
concentration
Concentration? Not really. Concentration is actually something, it's actually mass. Okay, momentum. If you, I believe in your high school, I'm not sure, you might have heard this term before, since high school, right? It has something to do with the mass that has a velocity, right? Exactly. Mass that has a movement, okay? So that is the momentum, all right? And if you want to consider if it can be transported, there must be something that drives these 3 things to transport, okay? So you have to have some kind of a measurable variables that can consider if this can be transported. So in terms of energy, in the previous example that I showed you here, we applied heat, or in this case is the energy, right? You can measure temperature along this distance here, okay? So in this case, measurable parameters or variables in terms of energy, that will be temperature, right? Because how do you measure if energy can be transported? there's no device or equipment that can measure energy, right? It has to be something with the temperature, okay? So if there are a difference in terms of temperature, for example, if I take this spot and this spot, which is the different locations, right? And if they have different temperatures, of course, there will be energy transported. You know what I mean? Okay. This spot and this spot, if they have different temperatures, the energy is going to transport. Okay. But if this spot and this spot have the same temperature, energy will not be able to transport because it has the same temperature. Okay, so there must be a gradient or difference in terms of the measurable parameters. Okay, so that these three things can be transported. All right, so in terms of mass, what would be the measurable parameters for mass? Concentration, exactly. That's very good. All right. If you remember the previous slide that I showed you, the iced coffee, right? To make a latte, iced latte, do you know how to make latte? Yeah, you add milk first, right? Well, milk first or coffee first. Yeah. You add milk first, and then you add coffee later, right? And what it's going to do? The milk or coffee is going to diffuse to the other phase, right? To each other, right? So the concentration, so we're talking in terms of the concentration, because concentration of milk has higher, I mean, in the phase of milk, it has a higher concentration of milk compared to coffee. Okay, so that's why the coffee can diffuse into the coffee phase. Oh, sorry, milk phase. Okay, and vice versa. Okay, I'll talk into details about this later. All right, but okay, for mass, the measurable parameters is the concentration. So if I have a system, let's say this system again, okay, and we have a concentration, higher concentration over here and lower concentration over here. So the higher concentration is going to be transported to the lower one, all right? And the last one is the momentum. What would be the measurable parameters? Velocity, exactly. So it's going to be the gradient or difference in terms of velocity in two different locations. Okay, so right here you can see that we have temperature, concentration, and velocity. That represents energy, mass, and momentum that is going to be transported respectively. All right, and all these measurable parameters is a function of time and position, like I said. Okay, in terms of position, like I showed you in the previous example, if you consider at a specific location within the system, okay, this location and this location, if it has different temperature, concentration, or velocity, there will be a transport of energy, mass, or momentum. Okay, but if both locations have the same or equal measurable parameters, or if it has the same temperature, has the same concentration or velocity at two different locations, there won't be transport going on. All right, and this also is a function of time as well that I showed you. Okay, because once it reaches the steady state, of course, the temperature, concentration, and velocity is going to change too. Okay, but like I said, that in our class, in my part, we're going to focus only at steady state. So it's going to make your life a lot easier. Okay. All right. So you can see here that um, um, that there are three types of transport: energy, mass, momentum. Okay, and the parameters that are involved with all three types is temperature, concentration, and velocity. In the next 7 weeks that we're going to meet with each other, we're going to set up an equation, okay, for energy, mass, and momentum, okay, in terms of as a function of temperature, concentration, and velocity, okay, under steady state condition, okay. It might sound easy, right? But it's not really. It's not really. Well, it might be, but it's going to be complicated, right? But yeah, we're going to be dealing with a lot of equations, okay, with temperature, concentration, and velocity. All right. All right, so now back to this slide again. I think you might have more idea or understand about this examples that I showed you here now. What kind of transport they are. Okay, let's see. What about this one first? The instant noodle. We're stirring up the instant noodle. Okay, what do you think? What kind of a transport phenomena do we have here? This one. Energy. Can you describe more? Explain like in terms of energy transport. Let's start with energy first because I hear the energy first. Yeah, there are a lot of that can be like a mix or combination, like energy and momentum transport, not just one. Maybe some of the system that consists of 3 types of phenomena. Yeah, what is it? Can you explain a little bit more about the energy transport? What again? The heat, okay, is to the environment, right? All right. Anything else? Momentum, okay. So momentum, you're stirring, right? So there's a movement of the mass. So mass right here, you can take a soup or the noodles inside, right? What about mass transport? Do we have mass transport in here? No? Maybe some of you shaking or nodding at the same time. Oh, yeah, yeah. You add all the ingredients, right, in the packet into the cup, right? You need to mix it well so that they are well dissolved into the soup, right? Yeah. So this, so you can see here that this example involved with all 3 types of transport, right? Energy, mass, and momentum, right? Maybe some of the examples or anything around you in your real life, there can be only one type of transport or 2 types or maybe 3, okay? It depends on, yeah, not it depends. I mean, you are the one who have to uh, understand and identify what kind of transport it is, okay? Because maybe in your homework in the future and in the exam, you might have to identify it by yourself, what kind of transport they are for that system, okay? So when I say system, yeah, it means that you have to define it because sometimes like in this example here, you can take a system anywhere, okay? If you focus on, for example, if you focus on the air surrounding it at the top of the noodles here, that could be a system too, right? So there could be only energy transport, right? Because you consider the air as a system. But if you consider a noodles as a system, there will be 3 types of transport. So different system, different defined systems have different types of transport. So it totally depends on the problem, okay? What you're focusing, okay? All right. Record. Someone is requesting to record. No. All right. Let's go. Why is not moving? All right. So any kind of system or any application, you will see that at the end, we will have a profile of temperature, concentration, and velocity as a representation of mass, energy, and momentum transport. In terms of temperature profile, concentration profile, and velocity profile here, what you get is something like this. You might have seen it before. So let's take a look at the temperature profile first, okay? This represents the energy transport, okay? Do you know what these are? heat exchanger, right? Double pipe heat exchanger. Okay, we have the inner pipe and the outer one. Okay, so what you if you measure temperature inside the fluid inside these pipes, okay, you will get the temperature profile along the length. Okay, so what you get is something like this on the graph. Okay, so this will show you that temperature profile is telling you a lot of things, okay, in terms of designing the heat exchanger, how long it should be, okay, in terms of designing and operation, like I said. So transport phenomena, maybe some of you might be wondering, why do I have to take this class, right? It sounds, uh, difficult or something like that. But in reality, transport phenomena is telling you a lot of things in terms of application. I mean, real life applications. So what you get from a temperature profile, something like this, you see that there are a gradient of temperature for the cold stream and the hot stream, okay, along the length of the tubes, okay, for the heat exchanger. So this is telling you that you can design, okay, the heat exchanger, for example, okay. And in terms of concentration, so if there are a gradient or difference of concentration of one location to, and the other location. So the higher concentration is going to be transported to the lower one. So what you get from this type of the system is the concentration profile that looks like this. So you can see that the concentration is going lower along the length of this system. Okay. So here you will get the temperature profile, concentration profile, and lastly is pretty similar, which is the velocity profile. So if we have flow in pipes, you might have seen this type of examples before. You know, right? Flow in pipes have two different types, laminar flow and turbulent flow. Which one is the laminar flow? Do you know? The top or bottom? Top one, right? It looks like a parabolic shape. Okay, this is the laminar flow. The bottom one is the turbulent flow. So you can see here that the velocity along the radius or diameter in the pipe is not the same, right? The velocity varies with the radius of the pipe. Okay, and since velocity has something to do with time, right? If comparing to higher velocity and the lower velocity, so it's telling you something in terms of, let's say, in terms of the kinetics. If you want to consider about the rate of reaction in terms of kinetics, have you taken kinetic class before? Yes. Okay. So you might have heard the rate of reaction before. So rate of reaction is dealing with time, right? So if you have a very high velocity flow, right? That means the length of time that the reactants, for example, staying inside the reactor is very short, right? Compared to the lower velocity, right? So that is going to impact the rate of reaction as well. Okay, so I'll give you the example of this in this slide. So what transport phenomena can be used for? Let me show you this example in a plug flow reactor. Do you know the assumption of the plug flow reactor? What does it mean by plug flow reactor? Let me see someone responding in the, oh no, okay. So plug flow reactor, the assumption is that everything across the cross-sectional area, sorry, it doesn't pop up. Huh? Hmm? Okay, so anything in this cross-sectional area here is going to be the same or equal, including velocity, concentration, everything. Okay, so if you have a reactants feeding on the left-hand side and you have reaction going on inside this reactor and products coming out. Okay, so within this cross-sectional area here, everything is the same. It's taken as the same, including temperature. Sorry, yeah, velocity, concentration, everything. Okay, but in reality, you know that when there's a flow in pipes or in a reactor like this, the velocity is actually not the same across this cross-sectional area, right? For example, if the flow is in laminar regime, okay, so the velocity profile is going to look like this. That means that the velocity at the middle of the reactor is going to be the highest, okay, here, and lowest at near to the wall, okay. That means that if you compare the length of time that reactants uh, remaining in the reactor, it means that the length of time that the reactors, sorry, that the reactants at the center of the reactor here is going to be shortest, right? The length of time is going to be shortest because the velocity is maximum. It's flowing very fast. That means that the length of time that the reactant is staying is very, very short compared to the one near the wall, which is velocity is lower, right? Slower. That means that the length of time is higher, okay? So in terms of the rate of reaction, uh, if you took the kinetics class before, you know that rate of reaction can be determined or calculated uh, based on this across this cross-sectional area, and it's average. Okay, the rate of reaction that you calculated is actually average across this cross-sectional area, but in reality, the rate of reaction across this cross-sectional area is not the same because the velocity profile is not uniform. Okay, do you know what I mean? Okay, any questions about this? So like I said, that transport phenomena, we look at things microscopically. So you can see that there are different, a lot of distribution within the system, okay? So like I said, that thermodynamics class, kinetics class, they take a look at things in a big picture. So they just average it, okay? But the approach of all three classes are all the same, all right? So yeah, to- so you can see now that even if we have energy, mass, or momentum transport, and we what eventually we'll get the temperature profile, concentration profile, and velocity profile. That is telling us a lot of things, right, in terms of designing and also operation, okay? But to solve that, to get the temperature profile, concentration profile, and velocity profile, there are several solving methods to do that, okay? Analytical, computational, and experimental, okay? In our class, of course, we're not going to do the experiment, of course not, right? In terms of experiment, we can do that by, for example, if you remember the first example that I showed you, we have a closed system that we apply heat on the left hand side, right? What we can do to solve the method and to derive the temperature profile is to take thermometer and measure the temperature at a specific point along the length, right? And that will get the temperature profile. That's the experimental approach, but we're not an laboratory class, right? We're a lecture class. So we're not going to do this one. Analytical, we're not going to do that either because analytical, for those of you who already taken the transport phenomena in your undergraduate program, you might have done an analytical before, okay, to solve it in differential equation, ODE, maybe PDE, all right? So in advanced transport phenomena, besides this tool, we're going to do computational, which Ajahn Grichard will be taken care of. All right. So in the next, after midterm, okay, he will be teaching you about computational methods. So we're going to use a software called ANSYS Fluent. Yeah, have you heard of it before? Maybe, yeah, some of you might have heard of it. Okay, so he's going to take care of this part. All right. So what is gonna look like is that if you have a mixing tank like this, you have a propellers, and you use the computational to solve this to see the concentration be very, very fundamental, okay, to derive the equation, to set up a differential equation for um, energy transport, momentum transport, and mass transport, okay? And once we set up the equations, Ajahn Gritchat will be taking care of the solving methods, okay? So you know the difference between the first section and the second sections, okay, in this course. All right. Any questions about this? What time is it now? 9. All right. We'll have a break too because this class is a 3-hour class. It's pretty long. So we're going to have a break, but maybe it's a few more slides, all right? Okay, so this is also the examples of practical applications, of course, chemical engineering related. The first one is like reactor, okay? You have a reaction coming in and also you applied heat to. So in this case, you can actually set up the equation for temperature profile because we have a heat applied to, right? And also momentum, velocity profile and concentration profile of the reactants or products in this case, okay? What about this one? The bottom one here on the left-hand side is like the absorber, okay? So yeah, and the middle picture right here is like a reactor which has a catalytic types of reactor. We have a catalyst in a sphere shape. So it depends what or where the system you're focusing on. So if you're focusing on the catalyst itself, you're going to see that there could be mass transport or even energy transport. Okay, but if you take a look at the gas phase that is flowing into this reactor as a system, okay, the transport will be different. Okay, like I said, that it's all yours. That if you consider the which system in within the whole system here, what you're looking at. Okay, all right. Okay, let's take a break so we can start this after this, okay? Let's take 10 minute break. Right now it's 10 a.m., okay? So let's come back and meet at 10:10, okay? Anyone in Zoom, do you have any questions? You can drop me a message. All right, I guess we can start. We'll see how it goes today. I'm not sure if we're going to finish all the slides today, but if not, then yeah, we're going to just move on to the next week, all right? So in a variety of applications that you've seen in the slides, before, you can see that they can be in any shapes, right? For example, in a reactor, in a plug flow reactor, for example, it will look like a cylindrical type of shape, right? But sometimes it can be in like a box or like a sphere, right? A system can be in different types of shape or geometry, okay? So in terms of setting up equations to derive a profiles for temperature, concentration, and also velocity, okay? We need to have an coordinate systems to define our system, okay? Of course, not all the applications can fit into the coordinate system, but we're going to try to find the closest one to fit into this type of coordinate system. So practically, there are three coordinate systems. So the first one is the Cartesian, which is the simplest one. Okay, it's like a rectangular coordinates. The other name that we can say, or the x, y, z that you've seen, right? X, y, and z. So all axes here are in perpendicular to each other. Okay. The other one is the cylindrical coordinate, and the last one is the spherical coordinate. Okay. So you can see by the axis. Okay. In Cartesian coordinate x, y, z, cylindrical coordinate is going to be r theta z, and spherical is going to be r theta and phi. Okay. So you have, and again, it's your job to define what the system that you're looking at to fit into either of this. Okay. Of course, the system that you're focusing on might not fit like perfectly into all this, but you have to select the closest one. Okay. For example, if I have like a parallel plate like this, and we have a flow through this parallel plates like this, do you think this what kind of a coordinate system you're going to choose for this system? Cartesian, of course, right? Why not cylindrical or spherical? Yeah, most of them, the surface is flat, and also they are also in perpendicular to each other, and it's going to be the simplest one. If you do the cylindrical, for example, it's going to be very complicated, right? So of course, in this case, you can set up like Cartesian coordinates for this system. Okay. What about this flow through pipe? We have a pressure gauge here too. Cylindrical, right? This is very obvious. So you can set up a cylindrical coordinate for this one. And what about this? A sphere, very obvious, right? Spherical type of reactor. There's also a practical type of reactor here in industry too. Of course, spherical coordinates, right? And what about this? This is actually fluidized bed type reactor, cylindrical, of course, but like I said, that we can define a system on our own, right? So if you focus on the whole reactor here, of course, you're going to select the cylindrical, like you said, right? But if I focus on the particles inside, solid particles, so let's say that it's like a catalyst inside, right? And we're going to take a look at the reaction going on, okay, on the surface of the catalyst, because it's the surface reaction, okay? If you focus on the catalyst, okay, as a system, what coordinate you're going to use? Spherical in this case. So if you think that if you take that this catalyst is in sphere shape, okay, so the system that you're going to use is spherical. Okay, so like I said, it totally depends on what you're focusing on. Okay, so yeah, the coordinate system can vary. Okay, what about this one? It's like a bubble column. You have a liquid feed at the bottom. Sorry, at the top, and gas at the bottom. Cylindrical, of course. And again, if you focus on the bubbles of the gas, you can use spherical coordinates. Okay. So in homework or in the exam, or of course in your thesis, I mean, when you do research and you might have to uh, uh, construct an equation to solve for the velocity profile, temperature, or concentration profile, you are the one to select the coordinates by yourself. And that means that you have to select the appropriate system first, okay, what you're focusing on, all right? So previously I talked about the coordinate system. That is like a location within the system, right? Because if I talked about Cartesian coordinate system, X, Y, and Z, is going to be like a location that represents in your system, okay? There are also three types of variables, which is scalar, vector, and tensor. Because in transport phenomena, there must be something transport, right? Either energy, um, mass, or velocity. So something has to move, okay? So within the coordinate system, there's something within the coordinate system, something's got to move, okay? So when something moves, we got to specify the direction for its movement too. So besides the position or location that is located in the system, you're going to define the direction where it is transported to as well, okay? So this slide, I'm going to show you three types of variables that it can be. So first one is scalar, next one is vector, and the last one is tensor. You might have heard all of this or some of this before. So let's take a look and or review it again, okay? Scalar is a variable that has only one magnitude, okay? For example, pressure, like atmospheric pressure, 1 bar, right? Something like that. It has no direction, okay? Or concentration, it only has a magnitude, okay? Anything else that you can think of that is a scalar? Mass? Yep. What else? There are plenty of variables that is a scalar. Temperature? Yes, yes. All right. Maybe density? Yeah. Okay. All right. So there are a bunch of scalar variables, right? So next is vector. Vector is something to do with the magnitude and also direction. Okay. So it has a magnitude and also specify the direction that is going to. Okay. For example, velocity, force. Okay. Velocity that is moving to. Okay. Force. What direction does force applying to? Okay. So any other variables that's in a vector? That's a vector? Yeah. Distance. Okay. What else? Huh? Displacement. What is it? This. Oh yeah, yeah, yeah. Okay. That's a good one. Anything else? Momentum. Momentum.
Acceleration,
Huh? Direction?
acceleration,
Acceleration. Okay, that's good. Okay. Huh? Speed. Speed is velocity. Yeah, same thing. All right. And the last one that you might have normally used or heard of is tensor. Tensor is a special type of variable that has one magnitude with two directions. Okay, we're going to go into details about these two directions later on. All right, but so you can see that all these three types of variables are different. Okay, and you have to use it correctly, okay, when you apply it in the equations, all right? So one magnitude, two directions. One example that that we use a lot in our class is the shear stress, okay, or tau, okay? So since we're going to derive a lot of equations, okay, and we're going to deal with a lot of variables in my part, okay? So to specify the variables that is in scalar, vector, and tensor, I am going to use only the capital for scalar, okay? For example, pressure, P, or concentration, C. I will just write P or C, okay? But if it's a vector, I'm going to underline it. one single underline, like velocity and force, like this, okay? If it's tensor, I'm going to double underline like this to represent that it's tensor. So when I write it in the equation, you know that, oh, this variable is vector or tensor or scalar, all right? If you take a look in the textbook, you will see that for scalar, they'll use just a normal capital letter. No, yeah, capital letter. But for vector, they're going to use, I believe, is a Greek letter or the italics, something like that. And for tensor, they're going to use like a bold letter, right? But since in my class, I'm going to write on my iPad later on, okay? I cannot make a bold letter, when I'm writing. So it's going to be hard. So I will represent by single line and double underline like this, all right? To represent that, oh, it's vector and tensor, okay? All right. So let's get into applying all these variables into the equations. But before getting into the equations, you need to understand the operation. Oh, sorry, no operator as well. Okay. First, if I have a vector A, see that is a single underline. Okay. If I have a vector A, which is equal to A1 delta 1 plus A2 delta 2 plus A3 delta 3. So you can see here that delta 1, delta 2, and delta 3 is actually unit vector for coordinate system that you select. Okay, so it can be in a Cartesian or cylindrical or spherical. So if it's a Cartesian coordinate, you can actually write as you can actually use it as an XYZ or IJK. It's all the same, doesn't matter. Okay, so it's going to be A1I plus A2J plus A3K. But if it's a cylindrical coordinate, it's going to be A1R plus A2 theta plus A3 Z, right? Same thing with the spherical R, theta, and phi, right? So it depends on the coordinate system that you're going to use, okay? So you can see here that A1, A2, and A3 are like coefficient, which is scalar because it just has a magnitude, right? And I don't underline anything, so it's scalar, right? But IJK, since it's the unit vector or coordinate systems, right? So it represents vector, all right? So since it's the Cartesian coordinates x, y, and z, if I have vector A right here, which is this arrow, okay? So you can see that it has a magnitude in x-axis of A1, all right? And y-axis, the magnitude is A2 and A2 and A3 in K coordinates, all right? And if I have another vector, which is B, okay? B1I, yeah, plus plus here. So if I plot it, it's going to be the other vector on the red arrow right here, okay? So it's going to have a different magnitude or coefficient B1, B2, and B3, all right, on the Cartesian coordinates, okay? All right. So let's take a look at the operator. So you know the different types of variables now, scalar, vector, and tensor. Now we're going to take a look at the operator. Operator is something like you operate in the equation. For example, plus, minus, multiplication, but that's the simple one that you you have used since you were very very young, right? But in transport phenomena we have more complicated, more advanced types of operators, okay, in the equation. So let's take a look at the scalar operator first. We have both scalar operators and vector operator, okay. So again, let's get back to the vector A. We have this one before, right? If I differential is a scalar operator, okay? So if I differentiate vector A right here, of course, I'm going to differentiate all the terms for in the equation. So it's going to be dA1I plus dA2J plus dA3K. Okay, and do you think the product of this equation is going to be scalar or vector? After you differentiate the product, is it in scalar or vector? Scalar or vector? Vector, of course. The whole term here, if you do this, it's going to still be vector because you still have I, J, K that define the vector, right? As I mean the direction. So it's going to be a vector. Any questions? Still following? Yes? Why the equation, the first one here? This one? Okay, so even if you differentiate the vector A, you can see that if you differentiate this term, and this term, the unit vector is still there, still presents, okay? So this term here is still vector. This term here is also vector and also vector. Sorry. There. Hold on. All right. If I have phi, excuse me, phi, which is a scalar, okay? Phi is scalar and it's a function of x, y, z, okay? Or I can write as a, in this term, phi x, y, z is a function of x, y, z, okay? If you can recall from calculus in your undergraduate program, I'm not sure, uh, in a chain rule, okay? If you differentiate phi as a function of s, and s is also scalar, okay, it can be distributed into this equation, into these three terms here, okay? d phi by dx, dx by ds, plus so on, all right? This is the chain rule. Excuse me. All right, so this whole term here, the product will be scalar, all right? Because each term is scalar, all right? So next one, previously we talked about scalar operator, which is differential, okay? Next is the vector operator. So if I have two vectors, vector A and vector B, okay? Both are in Cartesian coordinates, okay? If I have a dot operator, dot is a vector operator, okay? If I have A dot B, vector A dot vector B, okay? So I'm just going to write the whole term here. Vector A dot vector B, what is going to be, okay? You're going to multiply each term to the other, okay? For example, A1I multiply with B1I, like each one of this, okay? And please note that vector I dot vector I is equal to 1. I dot j is equal to 0. Okay. Do you think what will be the product for this dot? I mean, please write the equation, write the solution for this. Write the product for the dot of A and B. What is going to be if we dot them together? It's going to be A1, B1. So because you're going to distribute, multiply each pair of them, okay? So it's going to be A1, B1. Since A1, I multiply with B2J, it's going to be 0 because I dot J is equal to 0, right? So we'll end up having only 3 terms here. And a vector A dot vector B, what is going to be for the product, scalar or vector? Scalar, definitely. We don't have the unit vector defined anymore, right? So the product is scalar product, okay? Any questions from Zoom? Nope. Okay. All right. So previously we have this chain rule. Remember, we have d phi by the s here, and previously we also have a dot b, vector a dot vector b, which is this one. We just derived this, right? You can see that these two equation looks very similar, right? You can see here that, oh, this one looks like a1, this one looks like b1, a2, b2, a3, b3, right? The terms look very similar. So I can write d phi by ds that is equal to this term dot this term. Is that right? Let's take a closer look. Okay, I'll give you guys a few more seconds to take a look at this equation, how it is derived. Okay, it's just like the vector A and vector B dotting with each other, right? Because at the end, you will have the coefficient multiply with each other, okay? So if you have this two vector, this vector dot with this vector, what you're getting is that you have the coefficient of I multiply with this one, right? This one multiply with this one multiply with this one, which is actually the top equation over there. Is that right? Okay, so from here, I can take out the phi because phi is like a common term here for the first term. Okay, so in this case, I can take the phi out of this parenthesis. Okay, it's it's the same, right? If you plug it in, plug it back in, it's going to be this one, right? Okay, and you can see that I can switch to, right? Because this term here is scalar, so scalar can move anywhere to the front or back, doesn't matter. Okay, so if I take out the phi right here, okay, the last term is remains. Okay, so I will define this term here. You can see here that the one that I circle here on the slide looks like a differential. Is that right? Yeah, because it's just d by dx, d by dy, sorry, d by dz, okay? And this whole term here is called del. Looks like I'm crying, right? Del. And you can see that the symbol is like a triangle, upside down of triangle, okay? And I double line it too. You remember if I double line, what does it mean? Oh, sorry, one line. Sorry, one line. Vector. So del is vector. Why is vector? If you go back to this term, you can see that it is defined by ijk. So of course it's vector, right? So del with, so if I write on my iPad later, I will use something like this, okay? Like a single line to represent that is vector, okay? So right now we have derived that del. So del is like a differential with respect to the distance, okay? Distance x, distance y, and distance z, all right? All right, I'll give you guys a few seconds to write. Yeah, in this slide, you can see that I make some space for you guys to write on your own too. I don't put all the equations there so that you can write along, so that you're not falling asleep. Any questions about this? Are you guys still with me? Okay, all right, that's good. We're gonna take it slowly. It's good that the second semester, it's actually longer than the first semester. So normally this course is in the first semester, but this year is moved to the second semester. And it's good that, like I said, it's longer. If it's in the first semester, I will only have 7 weeks, but this semester I will have 8 weeks, so I can go slower. All right. I guess everyone is done. So this equation, okay, I'm going to make it short. All right, d phi by ds. Now this term is going to be just del phi. Is that right? Del phi. All right. Boop. Del phi right here. So previously we have derived a vector operator which is del. So del phi right here, okay? And let's take a look at the second term here that I circle, okay? Dx by ds I plus dy by ds right here. If I define vector r right here, which is equal to xi plus yj plus zk, okay? And since is it the term that I circle is in differential form, okay? So I have to make a differentiate with as a function of s, okay? So dr by ds is going to be actually the term that I circle. Is that right? So now we can rewrite this equation and make it short, okay? Saying that d phi by ds is actually equal to del phi dot dr by ds. That's it, okay? And yes, yep, ds x d here, yeah. What's the question again? Symbol s, yeah. Oh, it's just like a random variable. Yeah, it's scalar. It's scalar. Yeah. So what would be the product for this equation? Is it scalar or vector? Scalar or vector? Let's take a look at each. Del phi, is it scalar or vector? Vector, definitely. Why is vector? If you go back here, right? Even if phi is scalar, but it's defined with ijk. So phi, del phi is vector. What about dr by ds? Vector. So vector dot vector is scalar, definitely. Very good. Any questions from Zoom? Not yet. All right. Another operator, vector operator that we're going to talk about is divergence. Okay. The first one we have del, right? Next one is divergence. So divergence is actually the dot of the vector, okay, which is del is vector, right? And vector A is also vector. So vector dot vector is the product is divergence, okay? Can you write the product of del dot vector A? So we've already derived that del is equal to this term, right? Differential term here. And vector A is also this term, okay? Can you write a solution of del dot A? What would it be? see. Del dot A. Yeah, do not switch. Del dot A. Right? So this is del dot A. We'll let you practice the A dot del too. And we'll see if they're equal. Did you get the answer for that? Okay. Yes? What about you? Okay. So let's find out. Did you get this? Same result? Okay. So don't switch. Okay. So I dot I, of course, is equal to 1. So that will be dA1 by dx. Okay. So that is the answer for this. Okay. So is this scalar or vector? Scalar, definitely. Okay. Next, if we switch A dot del, do you think the answer will be equal to del dot A? Please find out for me. I'm going to walk around. I don't like staying still, okay? Will behave like an operator, right? Because it's B function, and when we count it, so it's going to operate this A1. Yeah. So when you switch, right? Yeah. So this two terms is going to switch. We'll find. Most of you are done. So let's see. Okay, so now if we switch to vector A dot del, what it's going to be? So of course, please don't switch. Okay, don't switch the spot. So it's going to be A1 dot I mean, multiply with the d by dx, since vector I dot vector I is equal to 1, right? So the product will be something like this, okay? So don't switch. Do not plug the A1 into the operator. It's going to be different, okay? So you can see here that del dot A is not equal to A dot del, okay? So don't switch. And you can see here that the product of the first one is actually scalar product, right? Because it's dA1 by dx plus dA2 by dy, something like that. But the product of A dot del is going to be scalar operator. It's not a product, it's an operator. You can see here that A1 d by dx. So you can see here that the whole term here is actually an operator, okay? So if you have a scalar or vector at the end, this whole thing here will be operating the variable at the back, all right? So you can see the difference, right? One is the product, the other one is the operator, but both are scalar. Any questions about it?
มีคำถามค่ะ
ค่ะ
ค่ะ
เชิญเลยค่ะ
product กับ operator ต่างกันไหมคะ
อะไรนะคะ
product กับ operator ต่างกันยังไงคะ
ตัวอะไรนะ Oh, okay. Product is like the final value for the equation. It's like a magnitude, okay? But the operator is like อธิบายไงเดียว it's like a plus, divide, multiply, something like that. The operator in the equation, the differential. You can see here that at the this here that I'm pointing on the screen right now. You can see that A1 is just like a coefficient, right? So it has not, it's just a magnitude, right? But d by dx is a differential which operates anything, okay? So if you have a variable, even if it's a scalar or vector, d by dx or d by dy or d by dz is going to operate or differentiate the other variable, okay? But it's not a product, it's not a magnitude yet. It doesn't have a magnitude, it doesn't have a value. Doesn't that make sense? เดี๋ยวขอเป็นภาษาไทยแล้วกัน ภาษาไทยแล้วกัน operator เป็นเหมือนแบบเครื่องหมายทางคณิตศาสตร์อะค่ะ เหมือนเอาไปดิฟเนี่ยเราเรียกกันง่ายๆเหมือนไปดิฟตัวนั้นตัวนี้ คือมันยังไม่มีค่าค่ะ มันยังไม่มีค่า เป็นคำตอบ เป็นจำนวนอะไรอย่างเงี้ยนึกออกปะแต่ product คือดิฟเรียบร้อยแล้วออกมาได้เป็นแบบ4สมมติอย่างเงี้ย4 18อะไรอย่างเงี้ยค่ะ แต่ operator คือแบบจะเอาไปบวก เอาไปคูณ เอาไป square root เนี่ยไอ้พวกเนี้ยเราเรียกว่า operator เนาะ ในที่นี้คือ differential นั่นเอง พอเข้าใจไหมคะ
เข้าใจค่ะ ขอบคุณค่ะ
ค่ะ Okay, any other questions? Did you have a question? This one? Yes. Yeah. Yeah. Uh-huh. Which one? This? This? No. This one is the operator. How come? Mm-hmm. I don't understand your. Yeah. Yeah. Mm-hmm. Right. Yeah. Uh-huh. Yeah, it's just a different arrangement. Yeah. So it's just the arrangement that you mentioned. So this one is an operator. So once you uh, do the dot, right, for the first term and the second term, this one is going to operate the coefficient for the second term. But this one, you can't just switch. Yeah. That is the key of the dotting, the vectors, two vectors. Mhm. So the key things that I'm trying to say in this slide is that when you dot the vectors, two vectors together, do not switch place because the arrangements are the arrangement matters, all right, in the equations, and it's going to affect the final answer. All right, we'll have a few more practices so you can practice. So earlier we have a dot del, right? Now we're going to operate the phi. Earlier we have phi before, right? And I'm going to let you find out the another term as well, which is del dot phi a. And the last one is del phi dot a. It's like all of them are different arrangements and in terms of operating each other. So please take your time and find that all out. All right. So previously you already got the hold on. Del sorry, a dot del, right here. Okay, a dot del right here. So in this case, a dot del, you just operate the phi. That's pretty straightforward. Is that right? You just operate the phi. So you can find this one pretty quickly, okay? Next one, find the del dot phi a. And last one is del phi dot a. And you think either one of these are equal, okay? All right, I'll give you like 5 to 10 minutes to find this all out, and we'll go through the solution together. Among this, I mean, one of these are equal. One pair is equal. Okay, how are we doing so far? All done? Just two? Oh, good, good. I just want a solution now. Do you need a few more minutes or do you want to go through the solution altogether now? Let's jump right into the solution, right? Okay, let's take a look at the first one. The first one is pretty straightforward since we already derived the a dot del previously in the previous slide, right? So we just operate the phi. So in this case, it's going to be, oops, sorry, it's too fast. Oh, no. It's okay. All right. So it's going to be operating the phi. So you can distribute into all three terms, all right? Everyone got that? All right, good. Next, del dot phi a. So you can see the arrangement is a little bit different, okay? So when you distribute all this, do it in the same arrangement, okay? So you start with del dot phi a. So this is the del, right? Dot phi a. So phi can multiply in all the terms of vector a, okay? Got that? All right, but it's not the final answer yet because these two vectors are dotting each other. So we're going to do the final product, which is equal to this one. Everyone got the same answer as me? Very good at the back. Very good. Yes, very good. What about people in the Zoom? People in Zoom, you have any questions about the second one?
No, it's the same.
Okay,
Same
great,
answer.
great. All right, I'll give you a few more minutes, a few more seconds to write this down. So the arrangement is the key, okay? Like I said, don't switch because it's going to affect the solution, the final solution. So now you can see that the product of the first term and the second term, are they equal? No, right? No. So let's find the third one out and we'll see which one is equal to the other. Okay. Are we clear on this? Can we move to the next one? All right. So next one is del phi dot a. Again, just distribute in the same arrangements. So del phi, we just operate, right? Because del is an operator with respect to, as a function of distance. So it operates phi, okay? Dot a, so this is the vector a. What is going to be the final product in this one?
I think same as above.
Is it this? You got this too?
I think it's
Yeah?
little bit different.
Did you
A1, I put A1 at the last, and here A1 is in the first.
did, so you get the d phi by dx and a1? It's actually the same. Is that right? Because you see a1, a2, a3 are coefficient and all are scalar, right? D phi by dx are also scalar, so they can switch. Is that right? Okay.
Okay.
In this case, it can switch. Yeah. Okay, good. So now you can see that which pair are equal? 1 and 3, right? So you can see here that the first and the third term here are equal, okay? I'm showing you this slide and let you guys practice, like give you guys plenty of time to work on this because we're going to be using these terms a lot in the next following weeks, okay? So please keep this slide in mind, okay? Because we're going to use it in a lot in the next following weeks. So even if we have a dot del phi or del phi dot a, they're equal. All right. Any questions? Okay. Yes. This one. Yeah, because this one is it's not just a phi, it's d phi by dx, right? Which is actually is the first is scalar, and A1, A2, A3 are also scalar. So of course, 2 times 4 are also equal to 4 times 2, right? You can switch the coefficient in this case. A1 by, no, you can't. No, you can't. It's going to be different. All right. Huh? Oh, you mean why A1 now because in the front? No, instead of that, they're equal because they're scalar. It's just a magnitude, right? Yeah, yeah, yeah. Oh, that's the what? Uh-huh. Phi A. Oh, you mean, let me see. Um, Same. This is same, but not, but not, these are not equal. All right, because they're operating the multiplication of phi A1. Okay, that's going to be different, but this one is correct. All clear? Okay. I love that we have interactions in the class. The dynamic in the class here is making me motivated, energetic, even if I feel very sick, right? But I feel like, oh, this class is fun. Hopefully for the next 7 weeks, we still have this dynamic. Hope you guys are not dropping the class. Do you guys have advisor already? Not yet? Oh, some of you might not. Hmm. Which lab are you in? Huh? Oh, you are in particle lab? Oh, who's your advisor? Oh, Shalida. Okay. Oh, is that the one who, that emailed us before? Oh, okay, okay, all right. Anyone else in particle lab? Oh, you are too? Do you have an advisor yet? Not yet. You decide and choose. Anyone else? Particle lab? All right. I'm just asking because I'm in particle lab. Anyone in catalyst? Oh, okay. It's only 2? What about the rest? In process control? Okay. Oh, who's your advisor? Sam. Oh, Pruitt. Right. I know that. And what about the rest? What about you? Polymer. Okay, that's nice. What about you guys? Oh, okay. Oh, polymer. Ajahn Sarawut. Okay. He's popular. I'm never popular. Never get selected. That's so sad. Never mind. All right. Last for vector operator, what do we have so far? We have del operator, we have divergence, and last one is Laplacian. Okay, last Laplacian is very simple and straightforward. So it's actually del dot del. So del is a vector, right? So vector dot vector becomes scalar, all right? So del dot del will become del square. So you can see here that del on the left-hand side here, I have a single line, right? It looks like a bold one. So once it's dotting each other, it becomes scalar. So that's why it no longer has a single line here, okay? So it's just a del square, all right? It's like a second order of differential, okay? So it's going to be like this, depending on the coordinate system, all right? So if I do the Laplacian of scalar S, okay, it's going to be something, oh, sorry, whoa. All right, it's going to be like this, okay? We might not get to see this one a lot, but yeah, just want to introduce you guys so in case you see it in some equations. All right. So far I have introduced you guys the coordinate systems, all right, the types of variables we have, which are scalar, vector, tensor, but the tensor we haven't talked about it yet. But we skip to the operators, which includes scalar and vector operators, right? So let's get back to tensor. Okay, so tensor that I mentioned earlier, that it has one magnitude with two directions. Okay, so the two directions can be shown in the picture right here. Okay, so you can see here that the delta is like a unit vector, right? So we have delta 1, delta 2, and delta 3. So if we pair them up, okay, we're going to have altogether 9 products, right? But I didn't put all the 9 products right here, okay? So just del 1, del 1, del 1, del 2, del 1, del 3, so on, okay? So the direction is going to follow the arrangement of the vector that presents in the form, okay? So if it's a del 1, it's going to, the direction is going to be similar like this, okay? If it's a del 1, del 2, the direction is going to present in different directions corresponding to the coordinate systems, okay? So when we put two vectors next to each other, it's not a multiplication, okay? Something like this, del I, del J, okay? It's a vector like this that I showed you in the picture right here. It's called dyadic product, dyadic product. And the product right here is tensor, all right? And again, del 1, del 2 is not equal to del 2, del 1, right? The tensor for these two products are going to mean differently, all right? I will show you later, okay? All right, let me distribute the terms for dyadic product into 9 terms totally, okay? Like I said that we have, it corresponds with the coordinate systems that we choose, right? So if I use the shear stress that represents as a tensor, okay, it's going to be tau 1, del 1, del 2, corresponding to the subscript of the shear stress right here, right? So if you distribute all the terms, you're going to end up having 9 products altogether, all right? So for example, if I have vector A and vector B, the same old ones, okay? And if I make it as a dyadic product, A1, B, oh, sorry, A, vector B. It's not a dot, it's not a multiplication, it's the dyadic product, right? So you end up having 9 products like this, okay? So you can see here that if we incorporate tensor, a variable that is a tensor in the equation, you end up having altogether 9 terms in the equation. It's going to be very, very complex, right? Yeah, but in reality, oh, sorry, I'll just make sure that you don't switch again. AB not equal to BA, all right? But I just want to show you that in most of the cases, I mean, most of the cases, we're not going to include all 9 products in the equation. For example, if I have del V right here, you can see here that del is a vector, right? V velocity is also a vector, right? Vector close next to each other is a tensor dyadic product, right? This is a tensor product. So if we distribute all the terms, we're going to have 9 terms totally, right? But like I said, that in most of the applications, if we are dealing with tensor in the equation or in the in the problem, for example, if we have fluid flow through pipes, okay, right here, what kind of coordinate system you're going to use for this one? Cylindrical, right? Because it's a fluid flow through pipe. Pipes is in cylindrical in this case. So if you distribute a tensor or the del V right here in terms of the cylindrical cylindrical coordinates, of course, in this slide, it show what I'm writing here is in Cartesian coordinates. So it doesn't correspond with the example on the right hand side. Okay, but if you write and distribute all the terms in cylindrical coordinates, you're going to have 9 terms as well. Is that right? In r, theta, and z directions. Okay. So fluid flow through pipes, you know that if I set the z direction over here and r is the diameter or the radius of the pipes, you can see here that the velocity is changing in r direction, right? I can say that velocity of the fluid is a function of radius, okay? Is it a function of theta? Like if I rotate it into different angles, the velocity is going to change? No. Is what about along z direction? Is velocities going to change along z direction? Yes. If it's flowing steadily. No, right? So in this case, velocity is a function of r only. Is that right? So in this case, if I distribute all these 9 terms here, sorry, this is in Cartesian, but if you write in cylindrical coordinates, you will neglect most of the terms, right? You will get only VR, sorry, let me write on the whiteboard. Sorry for the people in Zoom. So I'm writing on the whiteboard. So velocity is a function of r only, right? So that means that you get only dv by dr, right? Because dv by dz and dv by d theta are all equal to 0, right? Because it's not a function of z or theta. So that means that all other 8 terms are going to be 0. Okay, that means that you're dealing with only 1 term right here out of 9 terms. Okay, so what I'm saying is that even if there's a tensor in equation, that makes it looks a lot complex, right? Because we have 9 terms, but in reality, we can neglect most of the terms. Okay, for example, fluid flow through pipe like here, like this one that I'm showing you here. Okay, you can see that velocity is changing in r direction only. Okay, so we can neglect most of the terms in the equation. All right. Any questions? But some of the cases that we might have to have all 9 equations,
คือ
but
จะ
that
เหลือเทอมไหน
yes, yes.
จะเหลือเทอมไหนนะคะ
อ๋อ คือในเทอมเนี้ยค่ะ ในสมการที่อาจารย์โชว์เนี่ยมันเป็น Cartesian เนาะ คือมันไม่ได้เขียนอยู่ในcylindrical ค่ะ คือถ้าเขียนเป็น cylindrical เนี่ยมันจะเหลือแค่เทอม dv z by dr เท่านั้นนะคะ แล้วที่เหลือมันจะตัดไปหมดเลย เพราะมันเป็น0
โอเคค่ะ ขอบคุณค่ะ ค่ะ
ค่ะ All right. Any other questions? Okay. All right. No. So since we're going in transport phenomena, we're going to deal with fluid a lot, right? Because there's going to be a transport of fluid in terms of energy, mass, and concentration. So next we're going to talk about the relationship between parameters. Okay, since I just mentioned and introduced you with the shear stress. Shear stress is a part of the property of fluid. Okay, so if I have two parallel plates with the distance of y apart, like right here, and between these two parallel plates, we have a fluid, okay? All right, and if I define the system using Cartesian coordinates, so it's going to be x, y, and z, okay? To make it simple, at time zero, so at the very beginning, everything is staying still. Both plates are stationary, not moving, okay? So it means that the liquid inside is staying still as well, all right? So if I start pulling the top plate at velocity v, okay? So in this case, I specify vx2 because it's moving in x direction, all right? So if I start pulling the top plate with the velocity v, okay, vx, at time more than zero, what's going to happen? What do you think? If I start pulling the top plate, what's going to happen? What's going to happen with the liquid inside? The liquid starts to move along with the top plate as well, okay? So there's going to be some velocity of the liquid going on, all right? And the liquid that is in contact with the top plate is going to move with the same velocity too, and that we call no slip condition. Okay, so if you see the video clip right here, if you move or pull the top plate with the velocity, the blue line right here represents the velocity profile of the liquid. So it's going to move along, okay? And you can see that it's going to drag along the molecules of the water at the bottom too, okay? So the velocity profile across the y direction is not uniform, okay? The top one, the top one will be higher than that at the bottom one because the bottom plate is not moving, okay? So the velocity of the liquid that is in contact with the bottom plate is going to be zero at all times. So you can see here, this one is staying still, right? But once you move it further to the top, it's going to move along with the top plate, all right? So at the solid fluid interface, like I explained earlier, that the velocity of the fluid is equal to the velocity of solid, okay? And that is called no slip condition. We're going to use this kind of a boundary condition when we solve the equation, okay? And also in computational method that Ajahn Pritchard will be talking about as well, all right? So let's get back to it again. At time zero, everything is staying still. If you take a look at the along the y-axis, and if you can imagine that since we have a liquid inside, right, between these two plates, if we imagine that there are three chunks of water, number 1 to number 5, right here. At time zero, everything is staying still. All 5 molecules here are staying still along the y-axis, okay? At time more than zero, once we start pulling the top plate at velocity Vx, what's going to happen with the all 5 molecules, number 1 to 5? It's going to start moving with the velocity, okay? So number 1, the molecule number 1 here is going to move with the same velocity of the plate. So it's going to have the same velocity over here. And number 1 here is going to drag molecule number 2, and number 2 is going to drag along and so on to number 5, okay? You can see by the length of the arrow representing the velocity as well. So the longer the velocity, it means that the velocity is higher compared to the shorter one, all right? So if you keep pulling it, all right? So if I write the trend in the red line that's shown there, it's going to be the velocity profile along the y-axis, okay? And you can see here that the velocity of the water between these two plates are not equal, okay? They are distributed along y-axis, okay? And if you keep pulling the top plate until time becomes infinity or it reaches the steady state, the velocity profile is going to be like a straight line, like that. So the velocity profile is going to be like this, okay, at steady state. All right. So what we end up having right here, the red line here or there, is the velocity profile, okay? And previously, I mentioned that I used this system as a Cartesian coordinates, right, to represent the x, y, and z in these directions that's shown in the picture. Okay, so when you pull the plate, the top plate, the velocity of the liquid is going to move along with the top plate, which is in x direction. So if you distribute the vector v right here, you vy and vc are going to be 0, right? Because there is no movement of water in y direction or z direction. Is that right? Because you're only pulling the top plate in x direction. So water is not going to flow up or down or perpendicular to the screen like that, right? It's going to move along in x direction only. So when you distribute in three directions right here, you're not going to have Vy or Vz, okay? So at the end, you will have Vx is a function of y only, all right? So like I said earlier, that when we incorporate the coordinate system, normally we don't have all of the vectors in all directions, like Vx, Vy, Vz. We normally get only Vx or Vy or Vz, just one out of three, okay? But in some cases, there will be more than one, okay? Depending on how complicated it is. Okay, so let's take a look at the Vx is a function of y. We're going to derive an equation to represent and define the property of the fluid. Okay, so if you can imagine that we're pulling the top plate with the velocity Vx, right? Of course, we're going to apply force to pull this plate. So the higher force that we pull, of course, the velocity is going to be higher as well. Is that right? The pulling hard, the velocity is going to be high as well. If you're pulling very gently, the velocity is going to be pretty small. Okay, so force is proportional to velocity. Okay, but if we have consider the area of the plate as well, the larger plate and the smaller plate, the force that applied with respect to the area is going to affect the velocity as well. So if you have a larger area of the plate, okay, a big plate, for example, compared to the small plate, okay, the larger plate, the force distributed in the area will be small. Is that right? Because you have a larger plate, okay? And if you apply the same force, so the force that is applied to the all area of the large area is going to be small compared to the smaller plate, okay? So in this case, I'm going to use just not just the force, but force divided by area as well, okay? So it's proportional to velocity, okay? And if you consider the gap between the top and the bottom plate, it's going to affect the velocity that is pulling as well, okay? Do you think the smaller gap or larger gap, which one is harder to pull? Smaller gap and larger gap, which one is harder to pull? Larger? Smaller, yeah. Because when you have a very small gap between two plates, the liquid behaves like a resistance, both plates. between both plates. Okay, so it's harder to pull. Okay, so in this case, I'm going to write y, which is the gap between top and the bottom plates with respect, I mean, inversely proportional to the velocity. Okay, so we have a correlation, this one. Okay, so now let's make a complete equation for this one. So F divided by A is proportional V velocity divided by Y, or a gap. Okay, so if we make it a complete equation, so we're going to have a constant. So right here we have a mu, or viscosity. Okay, so force divided by A is equal to viscosity of the fluid times V by Y. Okay. So mu, or viscosity, represents the properties of the fluid. Okay, so this equation is actually called the Newton's law of proportional. Sorry. Vis oh, doesn't show. Oh, sorry. Okay, never mind. So F over A, force divided by A, is shear stress, if you can recall. Okay, but it's different to the pressure. So pressure is actually force exerted on the area, perpendicular area. Okay, but shear stress is actually force that is applied in parallel with the area that we're focusing on. Okay, so you can see here that this is the pressure of force acting on the perpendicular area, right? But the shear stress is actually force that is in a parallel with the area that we're focusing on. Okay, so it's different thing, but it has the same unit. Okay, force per area. All right, so F over A is actually shear stress. So shear stress right here. In this example, we're going to define it as a tau yx. So if you remember that shear stress is a tensor, right? And tensor has one magnitude with two directions. So two directions representing right here, yx. So what does it mean by that? When we pull the top plate, okay, the water, I mean liquid between the two plates here starts to move along the top plates as well. Okay, so the the force that is acting on the liquid that is in contact with the top plate is this shear stress, shear stress tau yx. So the definition is actually the shear stress in x direction acting on the area perpendicular to the y direction. Okay, so when we see the subscript of the tensor like this, we normally define from the right hand side of the subscript to the left hand side. So for example, like right here, tau yx is the shear stress in x direction because we're pulling the top plate in x direction. Is that right? X direction. Acting on the area is actually the area of the plate, okay, perpendicular to the y direction. So y direction is right here. So the area perpendicular is just like the area perpendicular to the screen, to make it simple. Okay, or you can say the other way is that the definition in terms of the tau yx is the velocity or momentum in x direction. Momentum is the mass with velocity, right? So it's moving in x direction. That is changing in y direction because the velocity is changing in y direction. Is that right? You can see the velocity profile here is changing in y direction. So that is the definition. If you take a look in the textbook, they can write two types of the definition, like I just mentioned. Okay, so you can switch the subscript over here because tau yx is not equal to tau xy. If you write a tau xy, it's going to mean differently. Tau xy is going to be shear stress in y direction acting on the area perpendicular to the x direction. It's going to be different. Okay, completely different. All right, so but in this case, in this example, it's going to be tau yx equal to mu v over y. All right. So since in transport phenomena, we look at things at a specific point. So we can define a small area, or we can define a system, like right here. This is the liquid between the two plates, right? If we consider only the tiny area here that I circle here, so you can rewrite the equation, right? As tau yx equal to mu dvx by dy, which is the velocity change in x direction with respect to y, okay? Because we're considering in the small area that I circle, okay? So it's going to be the velocity change in x direction with respect to y direction, all right? And that is Newton's law of viscosity that we just derived, okay? You might have seen this type of equation before, okay? It's a part of the fluid mechanics class, okay? So this is how it is derived, all right? And you can see here that any kind of fluid that follow this equation, it has to have a constant viscosity, right? Because if you take a look at this equation, mu is a constant, right? It's a constant. So the viscosity of the liquid must be constant, all right? Any questions about this? All right. So if you take a look at this equation, we can take a look at a real application. So on the left-hand side, the bottom here, we have a low viscosity type of the fluid, and the red one here is a high viscosity. So the high viscosity, you must apply larger force, or in this case, it's a larger shear stress, okay, in order for it to move, okay? And same thing with these examples. We have water, olive oil, and honey. So which one do you think that has the highest viscosity? Honey, right? And medium one should be olive oil, and the lowest one should be water. So in order to pour all three of the liquids here, honey should be hardest to move, right? So you have to apply a larger force in order for it to flow, all right? So that follows the Newton's law of viscosity. Okay, so this is the list of the viscosity for all types of the fluids. So fluids includes gas and liquids, right? So you can see that most of the gases have a lower viscosity compared to the liquid ones, okay? And for liquids, viscosity, I mean, for both liquids and gas, viscosity can change with temperature, okay? For liquids, when the temperature increases, the viscosity becomes lower, all right? I'll show you one example that you can imagine. When you cook, you put oil into the pan, right? You start heating up, and you leave it for a while before you add other ingredients into the pan, right? What's going to happen when you leave the oil in the pan for a while? It's going to move very easier, right? So that means that when you apply heat or temperature increases, the viscosity of the oil, or in this case, it's the liquid, becomes lower, okay? All right? And on the other hand, for gases, when we increase the temperature, the viscosity becomes higher, okay? It's the other way around, because if you can imagine that gas molecules are like are moving in Brownian motion, right? So if you apply heat or raising temperature, you apply the kinetic energy will be even higher. So the gas molecules will move around very, very fast and collide with each other, right? So once it collides with each other, they are harder to move. So when it's harder to move, the viscosity becomes higher, right? So yeah, the effect of temperature is differently for liquids and gas in terms of the viscosity. Okay. Yeah, same thing with the pressure as well. So if you imagine that you have some kind of a closed system and you pressurize the gas system, so the molecules become closer to each other. So that means that the viscosity becomes higher as well, right? So earlier I mean, we have derived the Newton's law of viscosity, and I mentioned that the viscosity must be constant, but this one has nothing to do with temperature and pressure. Okay, this one is for with I mean constant with time, with force, with anything else besides temperature and pressure. Okay, so if any fluid that has a constant viscosity we call Newtonian fluid. Okay, but if the viscosity is not constant, or I say that it's changing with time, force, or position, okay, this type of fluid is called non-Newtonian fluid. Oops, sorry, non-Newtonian fluid. So you might have heard this words before. Okay, what kind of fluid that is Newtonian fluid? Can you give me some examples? Newtonian fluid. Viscosity is constant. Water, yes. Anything else? There's a lot of things. What about oil? Huh? Newtonian, right? Yeah, because we're not talking about, oh, as a function of temperature and pressure. We're talking about viscosity changing in terms of as a function of time, force, position. Okay, so viscosity of oil doesn't change with time, force, or position. Okay, so oil is also Newtonian fluid. What about air? Air? It's also Newtonian fluid, right? So most of the liquid and gas are Newtonian fluids. But what are not? What examples are non-Newtonian fluid? Huh? Oh, ketchup, good examples. Yeah. Why? It changed with time, force, or position. Which one is that? Time? Force? Can you explain a little bit more? Yeah. Mm-hmm. Yeah, if you can imagine, if you are having food that you want to add ketchup, right? From kind of a glass bottle. If you just pour it, tilting the bottle, it will not flow, right? For ketchup, it's very sticky or it's some very viscous, right? But if you apply force by shaking very hard, so you apply force, then the viscosity will be changed, will become lower, so it will pour out of the bottle easier. Okay. Anything else for non-Newtonian fluid?
Butter or cheese?
Butter. Oh, good. Can you explain about butter being non-Newtonian fluid?
First of all, I think butter is very hard, and after that we have melted and its viscosity will be changed.
Okay. But it might have something to do with the temperature too, right? Like it's melting. Is that right? Yeah, I believe. Anything else? Huh? Toothpaste. Yeah. Can you explain a little bit more? Mm-hmm. Yeah, it's going to be harder, right? So it's changing with time. Very good. And maybe some painting, if right, if you leave it for a while, it becomes hard. Or anyone bake, if you're use the cornstarch before, if you mix it with water and you're not stirring it for a while, it becomes harder. So the viscosity is changing with time. Okay. So yeah, those are some examples of the non-Newtonian fluids. Okay. But luckily that, yes, blood, blood, like blood. Huh? Do you think it's non-Newtonian fluid? Yeah, because if we leave it for a while, it dries up, right? Yeah, it becomes like a solid. Yeah, that's very good. Excuse me. All right, but luckily for us that in our class we're going to consider only Newtonian fluid, because otherwise in the equation, if you can imagine that if we have viscosity mu as a part of the equation, and if it's changing with either time, force, or position, it's going to make the equation even more complicated, right? So we're just going to stick with the Newtonian fluid. All right. Okay, what time is it now? Oh, we have about 10, 13 minutes left. So I think I'm going to leave the rest of the slides to next week, all right? Because I don't want to cram all the contents now. So any questions? Yes? Coordinate system? Okay. This? The radius and what? You mean in terms of the theta? Uh-huh. I don't get. Uh-huh. Oh, okay, okay. I get what you mean. Right. For example, if we consider a long R, it will be like this point and this point, right? But what about theta, right? So it will be like this angle right here and the other angle right here, along maybe Z here. Yeah. All right. So if there's no other questions, then we'll meet you again next Tuesday. We will hopefully there's nothing wrong with the projector again. So yeah, I'll still be on Zoom again. So I believe that I'm not sure if the international students are coming by next week, but yeah, we'll be on Zoom again. But for Thai students, if you can come, please come to the class, okay? This class is not a hybrid class. It's actually in person or on-site class. So please come to the class. All right. If no other questions, then have a great rest of the day and see you next week.
ขอบคุณค่ะอาจารย์
ขอบคุณค่ะ
ขอบคุณค่ะ ขอบคุณค่ะ
ค่ะ